So today I'll discuss entropy, free energy, symmetry, and dynamics in the brain. The idea is to try to consolidate, let's say, these what seem like big notions or concepts, and specifically in the context on how they relate to dynamics in the brain, behavior, and mathematical modeling of that. And so I'll start a bit again with a bit of conceptual background and with this kind of big statement by Ilya Prigogine on, he says that the difference between being and not being is not an energy, but entropy. The price of the universe is to be paid in entropy. And what he really means in this exposition on the meaning of entropy is that he sees that the formulation of the second law of thermodynamics, in which Clausius introduced the concept of entropy, thermodynamic entropy, is to be taken as an entry point for resolving this big challenge, let's say, that classical science faces when trying to understand and capture individual biological existence and its concept and its complexity. And at the basis of this exposition is actually the interpretation of the concept of time, not as much as a repetition of a clockwork or degradation with aging, but actually as a process of constructive irreversibility. So a living system perpetuates its existence itself through entropy exchange with the environment. And as such, biology necessitates this inscription of time as a reversibility onto matter. Okay, and Ingvar, in also an old work on memories and the brain, sort of alludes to the ability of the brain to simulate memories of the future. And this is to sort of emphasize the role of irreversibility of the process of entropy production in interaction with the environment, that through which emerges the temporally polarized structures of the brain. So the brain navigates past, present, future because it has the irreversibility of time inscripted in its structure and spatially distributed in the anatomy of the brain. And this takes us to the notion of behavior, right? Because we want to understand what the brain is in reference to the function it's performing, and that's behavior. And so if we look into the literature, specifically in ecological psychology, you can think, first of all, there's not one definition of behavior, but most of them could sort of converge on that behavior is a set of internally coordinated actions that the organism performs in the presence of internal and external constraints or stimuli. And so the environment here plays an important role. And specifically, from a dynamical point of view, Scott Kelso formalized the field of what's called, or the framework of coordination dynamics, that says that you can capture behavior through its mirroring or its embodiment in the brain as the functional ordering of interacting neuronal components in both space and time. So here we're moving towards seeing the process of perception and action of a biological organism as one dynamical system per se. And then we ask the question, so how does this happen? How does this emerge? You have thermodynamics, you have entropy production through interaction with the environment, but still you have this ordering and coordination that's emerging spontaneously. Okay, and this is sort of, let's say, the general theme of large-scale brain modeling, right? We want to understand how does this emerge from what we know about the individual components. And so this theme of spatiotemporal spontaneous organization in complex system the first, let's say, mathematical study actually was in the work of, it's the theme that Ilya Prigogine actually contributed most in reference to chemical systems and what's called dissipative structures that emerge in far from equilibrium systems. And this is a famous example, if some people from the physics background would know, it's the Rayleigh-Benard convection. So it's a simple experiment. You take two plates and there's a fluid in between, and then there's a temperature gradient. So one of them is at a higher temperature than the other. And then you observe what's happening, and you have a parameter that you are tuning, and that parameter is that temperature gradient. As you increase that temperature difference, you will observe that structure starts to emerge, that the fluid, instead of going, I mean, if you increase it high enough, the fluid will become turbulent. But at an intermediate stage, you will see nice circular structures convection rolls trying to develop. Okay, and the idea here is that you have an instability. So the resting state of the fluid is losing stability, and out of that you have order emerging. So this emergence of complex but still ordered spatiotemporal structures is actually, there's a lot of mathematics there that was devised to actually understand that. And this brings us to the field of synergetics pioneered by Hermann Haken, who in the same, let's say, period that Prigogine was doing his work on chemical system, Hermann Haken pioneered the mathematics to try to understand how does spatiotemporal order emerge out of an instability in nonlinear spatiotemporal systems. And the idea is that so the basic, let's say, mathematical setup of this study is when you have an open system interacting with the environment through energy, entropy, information fluxes, you have a large number of weakly interacting microscopic elements, and the system is far from equilibrium. Okay, the idea is that as you change a parameter, there is some macroscopic order that emerges, such that now you can actually describe the macroscopic state of the system using a few order parameters. Okay, instead of having to keep track of what all the individual microscopic elements are doing. And this takes us to the mathematical formulation, which underlies the synergetics framework. And the idea is that as you vary parameters, you have spatiotemporal patterns emerging at critical points that corresponds to a bifurcation that is a sudden qualitative change in the nature of the dynamics, okay? Often through an instability of some equilibrium state that gives rise to another. And that's effectively, you get some low dimensional behavior, even though the system could be infinite dimensional, a continuum. Okay, and mathematically, you could understand this by looking in the neighborhood of the stable equilibrium state that exists before, let's say, the bifurcation or the transition. If you linearize the system, you look locally at the dynamics, you will see that you have a zero eigenvalue. So you have an eigenvalue that is actually switching sign in the real part. And you can expand the system in the neighborhood of that point. So here you have two neighborhoods, the neighborhood in state space near the equilibrium and in the vicinity of the bifurcation, meaning also the parameter is very close to the critical point. And then you will see what's termed the separation of timescales, meaning the flow in the space that's spanned by the slow eigenvalues, the eigenvectors that correspond to these zero eigenvalues. The timescale there is much slower than the fast other directions, so that the system, the trajectories will actually be enslaved. System will tend to collapse onto a slow invariant manifold. And then the theorem of central manifold, the central manifold theorem actually describes the mathematics rigorously in that situation. So just to sum up, okay, we talked about biological complexity, you have entropy production, irreversible processes, and nonlinearity giving rise to instabilities that give us actually order. And we said that from a mathematical point of view, the theory of synergetics, of emergent self-organization, gives us a sort of a mathematical framework to understand how does that occur mathematically. And for that, we said you have some local conditions. So in the vicinity of a phase transition, center manifold theorem tells us that we will have a separation of timescales. We will have the global flow collapsing fast to a neighborhood of an invariant low-dimensional manifold. Okay, and but now if we think of the brain, going back to our original theme, we're saying you have behavior, which is, when you observe it, behavior is low dimensional. I mean, the brain is a high dimensional system, but you have self-organized, coordinated actions in the space of behavior and reflected in the space of neural activity. So if we wanted to apply the bifurcation synergetics framework, this would be limiting, because then we were saying in order to explain how behavior emerge, we need to be in the vicinity of a certain equilibrium state of the brain, and with the parameters very well tuned to be in the locality of a critical phase transition. Okay, so we want something a bit more generic, and for that we go to another mathematical, let's say, process that could give rise to low dimensional manifolds in a high dimensional nonlinear system. And that is through proximity to symmetry. So this comes from classical Noether's theorem, if people from physics are familiar with it, which says that if you have a dynamical system that has a certain kind of equivariant dynamics, it has a certain kind of symmetry. Okay, so if you write down the equations for your system, and then you have some mathematical action that you do on the equations. Let's say you could have symmetry about the origin. You take x and y to minus x and minus y, and the equations are still the same. If you have a symmetry in the system, this is indicative of the presence of an conserved quantity. And in phase space and state space, this would correspond to an invariant manifold that when the system is on will tend to stay on. Okay, in the context of brain modeling, large brain network models, you can think of, you have a finite number of nodes connected through synaptic interaction, and a symmetry situation could be a fully connected network, same weight, or no connection at all. Okay, so in the fully symmetric case, you could actually start, we will have a finite number of fixed points, and you could permute the value of those nodes, values on the nodes, and you could still have a solution because it's fully symmetric. So this gives you a symmetry condition, let's say. Now, if you perturb the system, you break the symmetry slightly, okay? Instead of having a, as in the case of a symmetric, you have a finite number of fixed points. So you have an invariant manifold that's foliated by fixed points. If you break the symmetry, there will still be this sort of ghost of those fixed points, okay? But the system is not exactly symmetric. So you will not actually, if you start somewhere off these fixed points, you will not go simply directly to the manifold. You will collapse on a fast time scale and then maneuver in order to go to those fixed points. So Symmetry breaking or proximity to symmetry actually gives you another mathematical process through which low-dimensional invariant manifolds that corresponds usually to ordered spatiotemporal complex behavior actually emerge from a high-dimensional system. And so here just a small mathematical nuance that in the case of center manifold theory, we have the constraint of being proximity of equilibrium point and critical transition. So when we want to do the mathematics to see that flow on the manifold, we expand the system around, we linearize around an equilibrium point. That's why we are constrained in state space. If we were to take the scenario of a symmetry breaking, so emergence of flows on a manifold through symmetry breaking, we would be instead expanding our equations around that invariant manifold that corresponds to the symmetry condition. So we'd be instead expanding in parameter space around the parameter that corresponds to complete symmetry, and in state space, we would be expanding around that invariant manifold, which could have a global nature per se and not restricted to an equilibrium state. Okay, so this is sort of more powerful when we want to address global brain dynamics and behavior. And now just to go into a bit of into the mathematical details, what would that really look like? Let's just take the simple example of a 2D system that has a spherical symmetry, meaning that if I have two state variables, x and y, if I plug in to the equations x squared plus y squared equal to r squared, I will have actually zero flow. So the circle is a null line for the dynamics. Okay, in that case, if I start anywhere in state space, I will directly go onto that invariant circle. If I break that symmetry slightly, I will get the timescale separation. So I move fast onto that proximity or neighborhood of that invariant manifold, but then I will flow towards discrete number of fixed points that are actually the intersection of the new null lines, which are a perturbation away from the equivariant or invariant symmetry profile. Okay, so this is just exactly what I said. So let's try to look at really what that looks like. So this is a simple simulation. This is an example of a 2D system where you have the circular invariant manifold, and then we added this perturbation parameter mu, such that the null lines now are different, they're separate, and instead of a full circle of fixed points, we have a finite number of fixed points. That's the intersection of the null lines. And so you can see that the flow, you have this separation of time scale where you approach the old ghost of the invariant manifold very quickly, and then you have this flow, that's slow flow that's emerging on the manifold. Okay, and the structure of this flow on the manifold is actually structured or dictated, governed by the equilibrium points and their stability. So when you approach the slow manifold, you will move away from unstable fixed points and towards stable fixed point. So here we see the emergence of what's termed as structured flows of manifold. And of course, this is a very simple, well-engineered example that's probably not very relevant to the brain, but just to show the mathematical concepts. Now, of course, in the real world, you never have fully deterministic systems. And in the presence of small noise or stochastic fluctuations, what the system, you will, in the condition of this symmetry breaking or being close to symmetry, the deterministic structure is still there. You still have this separation of time scale, but then once you approach that slow manifold, the system will actually sample the slow manifold instead of just going to that deterministic fixed point. Okay. You can do this in higher dimensions. This is a 20-dimensional system with a embedded spherical invariant manifold. You look in state space in 3D, and it might not make sense what's going on here, but when you actually look at that invariant manifold that we perturbed away from, you'll see that the separation of time scale is there. And what was done here in the simulation is that the system was kicked away from the manifold again, and it will again approach it on a fast time scale and continue exploring the slow manifold at a much slower scale. Okay, so let's take a pause here after this math and just recap. We're talking about entropy, and we have entropic production, irreversibility, and complex nonlinear systems. And we discussed two possible mathematical processes through which you could get this low dimensional behavior out of high dimensional nonlinear system. The first was locality to a bifurcation point, and the second is through symmetry breaking, giving rise to structured flows and manifolds. But so how is this relevant to the brain? So on one hand, the structure, the symmetry breaking that I talked about in the context of a large scale network, right? That's one, let's say, school of thought on how to model the dynamics in the brain. People who are familiar with the virtual brain or other, it's very common to model the brain using a network where you use certain structural connectivity as the graph, and then the nodes correspond to the dynamics of neuronal populations. Okay, but then we have another school of thought, let's say, that talks less in terms of deterministic dynamical systems and more in terms of information theoretic concepts. Okay, still to answer the question of how does behavior, which is a low dimensional complex spatiotemporal structure, emerge from a highly complex nonlinear brain. And that framework is sort of one dominant theory in that framework is the free energy principle by Carl Friston, which sort of, instead of thinking in terms of thermodynamics and physics and energy and entropy in the sense of, let's say, what's used in fluids or solid mechanics, instead we think of the brain as a Bayesian inference system. Okay, so the free energy principle formulates mathematically how adaptive, self-organized systems can resist this natural thermodynamical tendency to disorder through entropy production and irreversibility of time. Okay, but and so through minimizing free energy, okay, which is also sort of the second face of the same coin of maximizing entropy, the brain realizes an internal generative model, which is updated as the brain interacts and acts on the world. Through perception, acquire new data that the brain can update its prior beliefs on what the brain is and what its actions on the brain can do. Okay, and sort of the bottom line of this work here is that how do we consolidate these two different viewpoints, which might seem that they're coming from completely different worlds, but I hope at the end of the talk you'll see that they're actually converging on the same idea. So in the first framework, we start with the model, right? We're assuming something about the structure, the mathematical structure of the model. We're assuming something about proximity to symmetry, And then we are seeing this emergence and the actual structured flow. So we're looking at the structure of the flow that is supposed to capture behavior. In the free energy principle, in this information theoretic framework, we don't assume anything about the form of the generative model. Okay, but we assume something about the process through which the model is updated and is emerging itself. Okay, and so the key here is that, remember when we talked about deterministic self-organization in spatiotemporal systems, we said that it's never really deterministic. You always have noise, and whenever you have noise or stochasticity, even if you have a very good idea about the deterministic laws or models that are governing the dynamics, you can no longer capture individual trajectories when you're thinking of solutions or what the system is actually doing on a global state. So now this leads us to evoke probabilistic concepts, okay, on how to describe the dynamics or the trajectories in state space. And this takes us to Edwin James' actually seminal work on maximum information principle, and its significance here enters from the fact that in this work, James consolidated the notion of entropy, on the one hand, as understood and introduced in the physical sciences, in the thermodynamics concept, consolidated it with the notion of uncertainty, with the information theoretic meaning of entropy. And he formulates a simple mathematical expression to what the information theoretic entropy, how can it be expressed in terms of probabilities of systems being, or state variables taking on certain values, but those state variables do not have to be the positions or speed or of a physical molecule or anything else. Okay, and the form it takes is this, and this is a summation of probabilities and products of probabilities with the natural logarithm of probabilities, and then the maximum information principle, maximum entropy principle, dictates that the system will actually, if you want to find out the probability distribution of a state variable that you are observing, you know there's stochasticity, then the probability distribution will take the form that maximizes entropy given the constraints that you know from the observations that you've made. Okay, and usually these constraints take the form of correlations. Example, you measure the mean value of a certain variable, and you know that this constraint, the probability that I'm looking for has to satisfy this constraint. Okay, so this becomes a simple mathematical optimization problem. We'll not go into the details of the derivation here, but basically it has to do with introducing Lagrange multipliers, which is a classical method in classical mechanics. And you can derive the explicit expression for the probability as with these lambdas, the Lagrange multipliers, actually being extracted from the deterministic constraints that come from the observations you make on the system. And notice here that the form of information entropy is actually the same mathematically as that from thermostatistics. And so now let's take a very simple example. If we had a 1D deterministic linear system, just one simple fixed point, x dot is minus epsilon x. We know that this is this corresponds to a certain potential function that's x squared, and if we actually observe the deterministic correlations such as the mean and the x or x squared, we can actually write down the probability distribution for the value of X under the influence of, let's say, stochastic Gaussian noise. And in this case, you just have a fixed point where the flow will actually approach. If you were to take two such systems and couple them, you can still do the same exercise. You can describe the state of the system, full state of the system, with the probability distribution that is again constrained by the deterministic correlations on the state variables. Now, these are two nodes, they're not communicating with each other. So the mean value of X, Y, there's no cross talk, is 0. So it's just a 2D Gaussian distribution, the probability of the system. But now if we allow the two simple nodes to actually influence each other, we add in a small coupling. So the mixed correlation term is no longer 0. And we write down the expression for probability distribution according to the maximum entropy principle. We can still derive the expression for the probability, but now there's this mixed term here. That's the XY term in the probability. If we actually simply split this exponential into two terms, the product of the exponentials, we will see that this comes out in the form of Bayes' theorem, where you have the probability of Y multiplying the conditional probability of X given Y. So this conditional probability actually is the free energy that the system is minimizing, and it manifests in state space as a distortion of the shape of the probability. Okay, so here we're starting to sort of bridge the gap between, if you have a system, deterministic system of coupled equations, in the presence of noise, you can no longer solve for trajectories individually. You start thinking of probability distributions, and you see that the system is actually minimizing a free energy term that is directly structured by the nature of the coupling between them. So this was a simple two linear nodes, coupled nodes, but now if we want to try to take this a step further and think of a mathematical system that's somehow more relevant to brain modeling, usually in whole brain network models, we parcellate the brain into finite number of brain regions, and then we model each brain region using a neuronal population model, using mean field or other phenomenological models. And often there's a generic dynamical feature of these neural mass models, that is that the system is bistable. So a brain region could be either inactive, silent, or active, so up or down. And a familiar example to some would be for example, the exact neural mass model derived by Montbrieux et al. In 2015. In that case, you end up with two equations for each neuronal population, one for the mean firing rate, one for the mean membrane potential. Okay. And if we look at the state space, the phase plane for this 2D system, you'll see that given the parameter value, that is the magnitude of the excitation input, the system could either have only down state or only up state, or the intermediate bistable state, which is more relevant to realistic dynamics. So we're going to extract from that an even simpler mathematical model that still has this generic feature of bistability, and that's the 1D nonlinear system here. X dot is x into 1 minus x squared. This is a 1D system, so phenomenological, but it still has this basic feature of bistability. And if we take that now and couple two of them, so each node alone can only be in a state of up or down. It has two stable equilibrium points, one unstable. If we couple two of them, if we take two of them, in the case of no coupling, the system will have a 3 by 3 number of fixed points, 4 of which are actually stable, so both down, both up, or the mixed state. If we look in the phase plane here, this would correspond to this nice cube. Now, if we add, sorry. Okay, I have this. Now we're going to add coupling to this system. It's going to be nonlinear coupling, but we're going to also rewrite the equation in a smartly designed way, such that when I add in the equation for x dot y squared times x, I split the coupling coefficient into g minus 1, okay, so that now for g equals 0, I actually have an equivariant system with an invariant manifold that is the circle. So this gives me 2 limit points. For g equal 1, I have 0 coupling. I have a finite number of fixed points. And for g equals 0, I have the completely symmetric case where the system, the 2D system, has a circular invariant manifold. And now I will break the symmetry. And instead of the fully equivariant situation, I will get the timescale separation, the flow onto the invariant manifold, and then the slow flow on the manifold driven by the structure of the fixed points. Now, if I add stochasticity to this system, in the presence of noise, I can no longer track individual trajectories, and I will have to instead look at the probability distributions. Again, in the no coupling, in the g equal 1, I have this composition of Gaussians. Each fixed point is independent. In the fully symmetric case, I have this invariant manifold at the circle that all trajectories are attracted to. In the intermediate case of the symmetry breaking, I have the timescale separation, and now I have a non-trivial invariant manifold populated by the equilibrium points that emerge, but it's actually distorted due to the coupling, that nonlinear coupling that we introduced. Now, if we do the exercise, try to derive the probability distribution and then split it so that we actually see the conditional probability using Bayes' theorem. Again, here, in this case of coupled bistable units, nonlinearly coupled, the free energy term again appears. The system is minimizing the free energy, which is taking the form of the structured flow that is dictated by the coupling. We can extend this to even higher dimensions, can go to 3D now. Instead of the plane, we are in the 3D cube. Again, with the special uncoupled case, we have a finite number of equilibria. As you break the symmetry, these equilibria will deform in space. The invariant manifold will emerge through timescale separation, and the structured flow is going to be directly dictated by the coupling. Now, the idea is that this sort of here has the basic ingredients, the dynamical ingredients that we see in large-scale brain models. We have nodes that can be bistable, that are coupled by a graph, and this simple mathematical exercise sort of illustrates how, through the symmetry breaking of the connectivity with the presence of stochasticity, we get timescale separation with the emergence of flow dimensional manifolds on which the flow is actually structured by the nature of the coupling as the symmetry is broken. If we go on to even higher dimension, then the coupling that we're talking about here usually comes from the connectum, the structural connectivity of the brain. Okay, and it's so again, it's an intermediate phase between the fully symmetric case where you have, let's say, zero coupling, where you have a finite number of, large number of equilibrium points. And as you increase the strength of the connectum, you're breaking the symmetry and the low dimensional structured flow and manifolds emerge. Now, I think I'm running out of time, but I'll just say very briefly that, okay, so we showed in a very nicely engineered mathematical example how this mathematical process of symmetry breaking could give rise to structured flows of manifold that are sort of the object of, that's mirroring behavior in the neural activity. We showed that in the presence of stochasticity, we have to think in terms of probability distribution. And we see then that the system is actually obeying the free energy principle. It's minimizing a free energy that itself is structured by the connectivity. Now, if we take this further and we actually simulate a whole brain network model using the Montbrieux et al. Population neural mass model on the nodes, and then we start increasing the coupling strength G using a typical connectum adjacency matrix from structural connectivity. When in the fully symmetric case, if we look at a low dimensional reduction using, let's say, projecting on the first two principal components of what's known as the functional connectivity dynamics matrix, we will see a high dimensional, just high dimensional, we don't see any structure. As we increase this symmetry breaking at certain critical points, this flow actually starts taking shape and we see signatures of low dimensional manifolds. If we further study the stability of the equilibrium point, we will find relationships between the flow on this low dimensional manifold and the stabilities of these, the gradients of stabilities that's directly dictated by the connectivity. So I don't have time to actually go into the details of the simulation work, but I just wanted to sort of show an extension of where this line of thought could go. And just to sum up the take-home messages is that you can understand the organization of deterministic and stochastic influences through the shape variations of probability distributions that are actually depicting the free energy that the system is minimizing, that's actually also generated by the couplings in the nodes. Okay. Now, just a small nuance is that the process of active inference, free energy principle, could be used to understand neural dynamics on several timescales. So in all what I've talked here, I've taken a snapshot in time where I've assumed that the mathematical model, the coupling, the dynamics is fixed, and I'm trying to see how does the behavior emerge from this model. But the organism could be, the brain could be minimizing free energy on a much longer time scale through learning processes, for example, or plasticity. And that would correspond to actually updating the actual parameters in the model. And so this doesn't contradict the fact that also for given parameters, the behavior is emerging through a minimization of free energy that's encoded in the structure of couplings. And finally, the relationship between the structured flow and manifold and the free energy principle could be really seen in the fact that the deterministic view out of which structured flow of manifolds emerge is sort of a conceptualization of that object, the generative model that is implicitly hypothesized in the free energy principle. So it's the spatiotemporal infrastructure in the abstract state space that is actually described by the structured flow on manifolds, whereas the free energy principle also tells you how that generative model itself could evolve on much longer timescales also. So I will stop here, and I hope I didn't go over time. Thank you.